Hello all. So we have started with unit 3 in which we were talking about regression algorithm, right? So when we were talking about different supervised learning algorithm, the first algorithm that we concentrate is on regression. Okay, so in the last few sessions I was talking about what is regression analysis, how do we measure linear relationship between independent and dependent variable with statistical model, and then we have seen how do we determine coefficients and then what is the significance of coefficients, right? So today in this session I would like to talk about types of regression. Okay, so before we actually start implementing a regression algorithm, we will look into different types of regression methods that are available. Okay, so depending upon the data that we work on, the regression can be done in various methods. The first one is linear regression. We have polynomial regression, we have logistic regression, we have support vector regression, decision tree regression, random forest, ridge, lasso, and so many. So depending upon the data that we work on, depending upon the problem statement that we work on, we choose one of the regression models. But just remember, regression is always chosen when the output variable has continuous values. Okay, so majorly in the subject we will be focusing on linear regression, logistic regression, and polynomial regression. Along with that, we will also discuss about the regularization methods, which are ridge and lasso. I'll explain you what is regularization and what is the importance of ridge and lasso regression. So let's look into these 5 regression models in detail. So first let's start with linear regression. So when I talk about linear regression, this is the most extensively used modeling technique which will actually give us the linear relationship between independent and dependent variable. When I talk about independent, they are x, that is input features. When I talk about dependent, it is y, that is the output variable or the target variable that we want to know about. Okay, so when we talk about linear regression, it is simply implementing the regression line and know which line actually fits the best amongst all the data points. Okay, so as discussed earlier, the linear regression expression is given by y is equal to mx plus c. Okay, so where c denotes the intercept and m denotes the slope, x is nothing but your independent variables, y is nothing but your dependent variable. Here I am adding an error term which is called as e, because depending upon this error term we'll adjust the slope and intercept such that the output variable will be matching with the input variables to get more accuracy or good accuracy or in line with the data. When I talk about this particular linear regression, this is a very simple line which will plot the data, which will actually plot the regression line upon the data points. As you can see here in the graph, the black dots are nothing but the data points and the red line is the regression line. Okay, so on x-axis and y-axis, we will be pointing out the x and y values, that is dependent and independent variables. So depending upon the data points, we are supposed to draw the regression line. Now when you look into this, the regression line can be this way, or regression line can be deviated this way, or regression line can be deviated this way. There would be multiple options of regression line that we draw, which actually depends on slope and intercept. That is equal to y is equal to mx plus c and m. Depending on that, the regression line would differ. Okay, so the best fitted line would be chosen as the final line, which gives you more appropriate results. Okay, so the best fit line is determined by varying the values of m and c. Okay, now when we look into this expression, we also have this error term. Okay, epsilon, it is generally represented by epsilon. This error term is nothing but the difference between the observed values and the actual values, the observed values and the predicted values. Okay, what are the actual values and what is the values that the machine learning algorithm has predicted. Okay, so if the observed values are too deviated from the predicted values, the error would be more. If the observed values if predicted values are near to the observed values or the actual values, the error would be less. So we obviously choose the less error, which means that the predictions that are made by the machine should actually match with the observed values or the actual values. Okay, so we have to choose the values of m and c in such a way that we get the best fit line. So when you get the best fit line, the observed values will not have much deviation with the prediction line, such that the error would be gradually very less. Okay, so when we talk about linear regression, again we have two major types of linear regression. One is called simple linear regression and the second one is called multiple linear regression. So when you talk about single variable input, okay, if suppose I have my output prediction based on only single variable input, okay, I choose simple linear regression. If you are predicting something based on numerous input values or numerous input features, then we go for multiple linear regression. Okay, so if you're going for simple linear regression, the expression would be y is equal to beta naught plus beta 1 plus x. For multiple linear regression, we'll have beta naught plus beta 1 x1. See here, I have only one input, right? Input feature. I'm talking about input feature, not the values inside that. Okay, so x is the input feature. So hence I have single variable. Here I have multiple variables, which is x1, x2, x3 and so on. So that is the reason we go for multiple linear regression. So here y is nothing but the dependent variable or the output. x1, x2, x3 are nothing but the independent variables, or we call them as predictors. B naught is the intercept and b1, b2 are the coefficients for the predicted term. Okay, and as told you, epsilon is nothing but the error term, which will actually gives us the difference between the actual output and the predicted output. Okay, next we talk about the second type of regression method that I want to talk about is logistic regression. Okay, so logistic regression, though I say linear regression is used when the output is continuous values. Okay, so logistic regression is also one type of regression, but here we choose logistic regression when the values are continuous, but we would like to fit those continuous values into two ranges. Okay, so we would like to have a sigmoid curve, logistic logod method, and then we convert those continuous values into either yes or no. For example, if I have values ranging from 0 to 1, okay, so I put a threshold of 0.5 and then say no matter whatever the values are there, if the values are lying between 0 to 0.5, they come under 0. If the values are lying above 0.5 to 1, they come under one category. Okay, so though we take the continuous values, that is the regression, we are trying to convert them into either yes or no. The probable outputs are only yes or no. I will continue or discontinue and all that. Okay, so depending upon this particular thing, we actually consider this as classification task, but the input values that we are taking are regression. That is the reason logistic regression comes under your regression algorithm, but not classification. Okay, so logistic regression is used when the dependent variable is binary. Okay, when you talk about dependent variable, I say it is output. Okay, so instead of predicting the actual value of the dependent variable, logistic regression actually predicts the probability that the outcome belongs to that particular class. Okay, so we choose the probability here, putting up a threshold value, we choose a probability. So based on the probability, we either select the category as yes or no, 0 or 1, false or true, and so on. Okay, so this is how the logistic regression equation is given as probability of y, which is nothing but depending on x. Okay, so here we write it as 1 by 1 plus e power minus beta naught plus beta 1 x. It can be one variable or two variable. Inputs can be one or two. Logistic regression could be found. Okay, so pre is the predicted probability that y equals 1, and then this is the exponential term that we are using in the linear combination of the predictors. Okay. So alternatively, we can also rewrite this equation as p by 1 minus p. Okay, so I say probability that y equals to 1 is given as p by log of p by 1 minus p, which we generally call it as log odds, or we call it as logit function. Okay, now as you can see here, though I have continuous values, okay, so here is a simple graph which explains whether a student will pass the test or not based on the number of hours he studies for the particular course. Okay, so depending on the number of hours he studies in the course, we will just have the probability whether passed probability is 25%, he may pass, 50% he may have chances to pass. So here I am giving the probability of whether he'll pass or not. See, the answer is yes or no, but I am deciding that based on the probability. If it is 65, 50 and above, see the cutoff marks for 100 is 35 in general, right? So 35 below it is fail, 35 above it is pass. Okay, it's something like that. So that is a probability that we define here. Okay, so where do we use logistic regression? We use logistic regression where we classify mail as a spam or not spam, and then predicting the likelihood of a customer buying a product, whether the person will see, looking upon the history of the customer's purchase or the salary of a person or the customer and so on, depending on various features, we will decide if a person can buy a product or not, predicting probability. Okay, so I can't say the person will buy or not buy, I can just give the probability, okay, yes or no in terms of the probability. The third type of regression that I would like to talk about is polynomial regression. Okay, so polynomial regression is simple like linear regression, but here the linear relation between the independent and dependent variable is modeled as a polynomial. Okay, which means that it can also allow non-linear relationship between the variables. Okay, so always the data may not be linear. I mean, when I talk about linear, if x is increasing, y is also increasing, or x is decreasing, y is also decreasing. Sometimes with x increasing, y may decrease, with x increasing, y may increase. Okay, the data would be non-linear as well. So in that case, we go for polynomial regression. When you often deal with data which is non-linear, we go for polynomial regression. Okay, so just understand that we use linear regression for a output variable which has continuous values, and x is dependent on y, either increasing way or decreasing way, linear relationship. Okay, we use logistic regression when the output variable has yes or no, true or false, binary predictions. We use polynomial regression when we have non-linear relationship between x and y. Okay, so here in this case, when you are talking about when I'm talking about non-linear relationship between the variables, we try to estimate the model coefficients. Okay, so depending upon the degree of polynomial, we will try to estimate the model coefficients. And here in this case, you see, I am modifying the equation into y is equal to beta naught plus beta 1 x plus beta 1 x square plus beta 1 x cube and so on. So x1, x2, x3 would be the higher degree terms, and d is nothing but your degree of polynomial. Okay, so here 1, 2, 3 that I am giving is nothing but the degree of polynomial. So depending upon the degree of polynomial, we calculate the coefficients and see in what way the data is completely non-linear and how do I predict my output based on the given non-linearly spread input data. Okay, so as you can see, sometimes the values, as x increases, sometimes the values are increasing, sometimes decreasing, sometimes increasing, sometimes decreasing and so on. This is called nonlinear data. When you talk about nonlinear data, I may not have a straight line curve. I don't have a straight regression line, but I'll have a curved regression line when you talk about polynomial regression. Okay, now when do we use this? Suppose you're predicting the profit of a company based on its advertising budget. Okay, sometimes the budget for few products would be more, sometimes the budget for few products would be less. Okay, so and solely sometimes the company profit may depend on the budget, advertising budget, or may not. So hence we cannot actually say there's a linear relationship. Okay, we may have the investment decrease or increase at certain point. For example, when I talk about, even if I do so much advertisement, okay, if it is non-festive season, the sales may go down. Even if I don't do any advertisements, but during festive seasons, obviously the sales goes up, right? So advertisement may not solely decide the profits of sales or the decrease in sales. Okay, so this kind of data that we work on, where x and y are not at all linear, then we choose polynomial regression. Okay, so here when you talk about the expression, we have b naught plus b1 into budget plus b2 into budget square, beta 2 into budget square and so on. Okay, when you talk about use cases, we use this in predicting the trajectory of a projectile, where the height is the function of time squared, sometimes may be dependent or may not be dependent, and modeling economic variables where relationship between variables are actually non-linear. Okay, there are so many applications where x and y are nowhere related, completely non-linear, where we choose polynomial regression. Okay, so I would like to quickly compare these three regression models: linear, logistic and polynomial. So when you want to predict a continuous value, we go for linear. When you want to predict binary or categorical value, we go for logistic. When you want to predict a continuous values but the data is non-linear, we go for polynomial. Okay, so dependent variable has continuous values, here categorical values, here also it is continuous values. When I talk When I talk about house price, there would not be much difference in house price and salary. Salary of a person based on experience would be, you know, mostly linear, because as the experience increases, the salary would increase. Very few abnormalities. But when you talk about sales and profit in all these cases, okay, though the output variable has continuous values, sometimes abnormalities or discrepancies happen. So in this case, we go for polynomial regression. Okay, and when you talk about type of relationship, it is linear. We go for log-odds, that is logistic relation, and here we use non-linear relationship between independent and dependent. Okay, when you talk about output, the output variables has continuous values. Here we go for probability. Here also it is continuous. When I talk about linearity, assumes linear relationship. Logit of the probability, non-linear relationship. Example use cases: predicting house prices, predicting if a customer will buy product or not, yes or no, binary output. Predicting company profit based on advertising amount spent. Okay. Now, not just this, apart from linear, logistic, and polynomial, we also have other types of regressions. When we talk about ridge and lasso, okay, so ridge and lasso is a type of regression models with regularization techniques, which will actually prevent overfitting and all that concepts. Okay, so when we talk about overfitting, as I told you, the entire data that we feed to the machine learning model would be divided into training data and test data. Okay, training data is used for training the model, test data is used for testing the performance of the model, right? So the machine may work well with the training data but may fail with the test data. So that is where we have overfitting and underfitting concepts coming into picture, cases coming into picture. Sometimes the machine may not work well with training data itself. Okay, obviously it will not work with test data. So this is called as underfitting. Okay, so in order to overcome in order to prevent overfitting and all that, will be using regularization techniques, for which we will opt for ridge and lasso regression. Along with that, combination of ridge and lasso is nothing but your elastic net regression. And when we were talking about linear regression with statistical models, we have already seen ordinary least square method. Okay, these are different types of regression models that we actually use in our day-to-day machine learning algorithms when we talk about supervised regression learning methods. Okay, most famous are linear, logistic, polynomial. Sometimes we'll also be using ridge and lasso. Okay, so before we actually go with ridge and lasso, we will discuss about what is regularization. Okay, so regularization is very important concept in machine learning. It is basically a technique that is used in machine learning and statistics to prevent models from overfitting, or to prevent models from becoming too complex. When I say complex, they work well with the training data but they don't work well with the test data. So in that case, to avoid that, okay, we go with the regularization. So when I talk about overfitting, the model learns not just the underlying patterns but also with the noise. Therefore, when you get new data or the test data or unseen data, the model may not perform well. So regularization will actually address this problem of overfitting by adding a penalty term. Okay, so for adding this penalty term and then shrink the model coefficients, basically the goal is to create a generalized model that works well on training data and test data as well. Okay, so for that case we use regularization. And when I talk about regularization, there are two important regularization types. One is called as L1 regularization, second one is called as L2. So that L1 regularization is nothing but lasso regression that we were talking about. L2 regularization is nothing but ridge regression that you are talking about. Okay, so L1 regularization, I was talking about penalty points and then equal coefficients, right? So L1 regularization will actually add that penalty equal to the absolute value of the coefficients to the loss function, okay, to reduce the loss function or the epsilon or the error that I was talking about. This results in some coefficients being reduced exactly to 0, which means that some of the features are actually removed. Hence, proper feature selection will be done, and then overfitting problem can be avoided. Okay, and then next come, for example, imagine you're building house prices using features like size, number of rooms, location, year build, and so on. Okay, so when I see all these four input features, I don't think year build might have good effect on the output. So when I talk about L1 regularization, it will actually assign zero weight to ear welt or simply remove that and considers only these three important features such that overfitting problem may be reduced. Okay. Next, when I talk about L2 regularization or ridge regularization, it will add penalty equal to the square of the magnitude of the coefficients. Previous case, when I talk about linear regression, it is absolute value of the coefficients. Here in ridge regression or L2, it is square of the magnitude of the coefficients. Okay, so unlike L1, the L2 regularization actually shrink the coefficients but not eliminate them. Okay, so in the previous case we were eliminating them, right? So here it will shrink the coefficients instead of eliminating it. Okay, so when you have multicollinearity, when I talk about multicollinearity, the features are highly correlated. Okay, so the output may also be dependent on the number of the year built. Okay, so if the house is too old, the price may be less. Okay, so if all the features are too dependent on each other or correlated, when we can't delete that feature but make some adjustment in that particular feature, we go for this particular regression, which is called as ridge regression or regularization. Just remember, when you have multicollinearity, we go for L2 regularization. Okay, so when multiple features are correlated, the coefficients of the linear model can become unstable, leading to overfitting. So L2 regularization will actually help us with that. Okay, suppose you are predicting employee salaries based on experience, education, job role, company and all that. Okay, sometimes features like experience and job role may be highly correlated. So instead of removing the any of the feature, it will shrink the coefficients and then it will avoid too much influence on the output prediction. Okay, so this is all about L1 and L2 regularizations. I would like to compare here absolute values of the coefficients. Penalty action is absolute value of coefficient, here it is square. Effect, some coefficients become exactly zero, that is feature will be totally eliminated, but here they'll shrink the coefficients. When I talk about feature selection, yes, we can eliminate irrelevant features. No, we will retain all the features but shrink the coefficients. Use case, when feature selection is needed, when feature selection is correlated or multicollinearity, we go for L2 regularization. Leads to sparse model, fewer features, retains all features which reduces overfitting, simplifies the model by removing features, reduces overfitting without feature elimination. Okay, so this is all about ridge and lasso, regularization and ridge regression, lasso regression. So these are the 5 different types of regression that we often use in machine learning models. Linear, we have simple linear, multiple linear, we also have logistic regression, we also have polynomial, we also have ridge regression, we also have lasso regression. Thank you so much.